Alright, welcome back. In example 2, we're going to look at, instead of a graph of velocity, we're going to look at a graph of the position of the particle and answer a bunch of questions based off of this graph. This can be a little bit more complicated with some of the questions that we're going to ask. And so let's take a look and see what we have. But again, first thing I do, I make sure I understand what the graph is. This is a graph of position moving along the x-axis. So this is a graph of x of t. And therefore, velocity is going to be represented by the derivative of this graph, since it's a position graph. Acceleration would be represented by the second derivative of this graph. And so any questions we're asked, we're going to answer based off of those relationships. So our first question is, when is the particle's velocity positive? Okay, since this is a graph of position, velocity is the derivative, and therefore velocity is represented by the slope of this graph. And so I'm looking for places where the slope of the graph is positive. It's positive here, and it's positive here, it's positive here, it's positive here. So all of those time intervals are places where the velocity is positive. So I'm going to identify all of those. Got from 0 to 1, and from 3 to 5, and then from 6 to 7, and from 9 to 10. Velocity is derivative of position, and this is where slope of the position graph is positive. Alright, question 2, when is the particle's velocity negative? So we're going to deal with the converse situation here. Wherever the velocity is negative is where the slope is negative. And so it's going to be on those time intervals there. So we've got from 1 to 3, and from 5 to 6, and then from 7 to 9. And so here we go again. Velocity is the derivative of position. And this is where the slope is negative. Okay. Question number 3. When does a particle change directions? Everywhere where the velocity changes sign from positive to negative, negative to positive. So we've got a fairly long list here. Got it time 1, 3, 5, 6, 7, and 9. Alright, these are all the places where velocity changes sign. Okay, alright, now I'm going to erase those highlights and turn to questions 4, 5, and 6. Alright, question 4. When is the acceleration positive? So acceleration is the second derivative of the position function. So it's going to be represented by the second derivative of this function. And in order to interpret this, we've looked at two different ways really of interpreting the derivative from a graph. We've looked at it as the slope of the graph, and we've also looked at it as the change in the graph. And if we put these two concepts together, that gives us a good physical interpretation for the second derivative. Second derivative is represented by the change in slope. So we're looking for, to find where the acceleration is positive, the change in the slope of the position graph. So we want the change in the slope of this graph to be positive. In other words, the slope is becoming more and more positive or less and less negative. All right? So let's kind of analyze as we go along this graph. Here, the slope is getting less and less positive. It's decreasing. The slope is decreasing, the slope is decreasing, the slope is decreasing on that entire interval. So the acceleration is not positive there. On this interval, the slope is constant. On this interval, the slope goes from being a large negative value to a smaller negative value to a zero value to a positive value, and then right around here the slope starts to decrease again. And so that time interval right there is going to be one where the acceleration is positive. There's one other place, starts right about here, it goes here, where the change in the slope is positive. It's going from being a negative value to a less negative value to a zero value to a positive value. And so those are going to be our time intervals where the acceleration is positive. So 5 to about 6.5. And from, looks like about 7.5 to 10. And to describe this, the slope of the position graph is increasing showing a positive change in slope since acceleration is the second derivative of position. It is represented by the change in slope. All right. For question 5, when is the acceleration negative? We're going to look for places where the slope is decreasing, and we already kind of highlighted what goes on in each of these intervals. On this interval, the slope is decreasing, and on this interval right here, the slope is decreasing. And so from 0 to 3, and 6.5 to 7.5. 0 to 3, and 6.5 to 7.5. This is where slope is decreasing. Indicating a negative change in the derivative. So a negative value for our second derivative. Slightly different way of explaining it that time. Both of these would be pretty good explanations of what's going on here. And the last question, when is the acceleration 0? And that's going to be indicated by this segment of the graph where the slope does not change. So from 3 to 5. The slope of the position graph which represents velocity doesn't change in this interval. So the derivative of velocity which is acceleration is 0 here. Right? So there's a lot of different ways that I can use my words to describe and justify the scenarios. As long as your explanation is valid and something that someone could read it and go, yes, they understand why this is what it is, that'll be an okay explanation for us. And that's the end of this lesson on graphical interpretation of particulate motion. See you guys next time. Have a great day.